With untyped mo, we're able to implement recursion without changing the language. One of the ways we encoded recursion is here, with self-application. We wrote a makerec helper function and then used that to write recursive functions like Fibonacci. If we try to do the same thing now in typed mo, we find that this encoding doesn't work out. And that's because now we need to supply a type for every variable in this program. Most of these types we can fill in, no problem. But the issue comes in these red ... dots here. This variable fx needs a type that says fx can be applied to itself. But with our current language of types, this would require an infinite unfolding. As a first try, we could say that fx takes in an int-to-int function and then returns another int-to-int function. But then when we go to apply that fx to itself, we would need an extended type for fx on the left to take in something that has exactly the type of fx and then at the end returns an int-to-int function. Long story short, we're stuck here. Nothing works in place of these ... dots. We don't have a type to fill that in. And in fact, we're stuck for a fundamental reason. If we could encode recursion, then we would be able to write programs that can run in infinite loops. But in typed mo, the types make it impossible to have a non-terminating program. That's a theorem for the simply typed lambda calculus, and typed mo is basically the same as this lambda calculus, but it has a few extra primitives. What can we do for typed recursion? Let's extend the language. When encodings fail, it's time to build in a new primitive. We'll now add in letrec as a core form. First, we need to extend our grammar. Letrec will take in a symbol, a type, and two expressions, and that's all for the extension. We're not going to change the language of types down at the bottom. For our abstract syntax, we'll need a letrec e variant, and this needs 4 fields to hold the parts from our grammar. We'll also need to change the type for bindings that we hold inside the environment. That's because with letrec, this name needs to be available inside the right-hand side. It needs to happen before the right-hand side gets reduced to a value. So we'll change bindings to hold a value, which is a box of an optional value. This can start off with none for the letrec right-hand side. And then before we go to interpret the body, we will use setBox to change that some value. And with that, we're ready to extend the interpreter. Interpreting a letrec e, first we set up a new binding, and then we extend our environment to say that n points to this b, this box with nothing. Then we can interpret the right-hand side in the context of this new environment, and we'll use that value to update b in the environment again. Finally, we interpret the body in the new environment. This should all be familiar. The new part comes with type checking. Here's the typing rule we want for a letrec. And the key here is that we extend the environment with x bound to tau 0 in both cases of type checking. First, we type check that E0 right-hand side expression in an extended environment. We need to make sure that this E0 has type tau 0. Second, we check the body expression, and we use the same extended environment for that. And the body needs to have type tau 1, in which case we can conclude that the whole letrec has type tau 1. To turn that into code, we need to type check the right-hand side and the body, and we need to do that type checking in an extended environment. We use the same extended environment for both of those cases. This environment binds n to the right-hand side type. With that, we're almost done. We just need to know that when we type check the right-hand side, the type that we get back is equal to the right-hand side type from the annotation. If it is, we can go on and type check the body. If it's not, raise a type error.